Most open-source vision language models operate under a specific structural limitation. They ingest one image, pair it with text, and produce a textual output. This rigid mapping prevents complex visual reasoning. If a model can only process a single isolated snapshot, it cannot perform multi-turn conversations, compare two different images, or learn from a sequence of visual demonstrations. The alternative is an autoregressive framework that maps arbitrarily interleaved sequences of images and text into a continuous stream. Instead of an isolated prompt, the input becomes a flowing document where pictures and paragraphs are mixed together in any order. DeepMind proved this in-context learning capability with their Flamingo models. However, the architecture and the training data remained proprietary, unavailable to the broader research community. Flamingo is an open-source replication designed to reverse engineer that 9 billion parameter stack using public components. The interface allows raw images and text prompts to exist in the same sequence. A user can input a prompt containing this image of a raccoon in a spacesuit embedded mid-sequence, followed by a request for the model to describe the scene. By integrating specific public components, the project proves that in-context multimodal foundation models can be built outside of closed corporate labs. The architecture does not train from scratch. Instead, it preserves the pre-trained representations of existing foundational models. During extraction, a frozen clip vision transformer extracts image patch features, feeding them into a trainable perceiver resampler. Running parallel is a frozen language model. Trainable cross-attention modules bridge them, inserted every fourth layer to inject visual context. The researchers tested different text backbones, including standard base models and instruction-tuned variants like MPT-1B Instruct. The data shows that language instruction tuning provides a measurable performance lift. Capabilities learned purely on text instructions actually transfer to vision language tasks when the new weights are integrated into the stack. The replication relies on these precise, trainable bridges placed between frozen pre-computed encoders and decoders. Replicating Flamingo required finding public equivalents to proprietary datasets like Align and M3W, which are currently unavailable to the public. The team used Lion 2B for single-image text pairs and Multimodal C4 for interleaved sequences. This chart reveals MMC4's structural imbalance: long text strings but exceptionally few images. To compensate, researchers pre-process sequences by inserting an image token exactly where a visual appears. They then add an end-of-chunk token, mapping the precise boundaries of each cross-modal relationships. Forcing a language model to respect visual context requires explicitly hard-coding these spatial boundaries directly into the token sequence itself. The extremely sparse distribution of images within the MMC4 dataset directly impacts how the cross-attention layers learn during the training. This graph tracks training loss over 60 million samples. Lion 2B loss decreases steadily, but MMC4 loss flattens almost immediately. Because MMC4 features long paragraphs between images, the model accurately predicts text without referencing visuals, effectively bypassing the cross-attention modules. This dynamic encountered a hardware hurdle when scaling the 4 billion parameter model using the Red Pajama backbone. To distribute the model across 64 GPUs, the team used fully sharded data parallel. However, severe technical complications with this parallel strategy forced the engineers to freeze the randomly initialized image and end-of-chunk boundary embeddings. Freezing these boundary tokens triggered a 12.1% accuracy drop in zero-shot visual question answering. Trainable boundary embeddings are required for the model to function. Sacrificing these weights for hardware efficiency breaks the model's ability to reason about the interleaved sequence. To benchmark the replication, researchers evaluated Flamingo across 7 vision language datasets. They measured in-context learning by testing the model's capacity to scale across 0, 4, 8, 16, and 32 shots. This trend graph tracks performance from 0 to 32 shots. The 9 billion parameter Flamingo model mirrors proprietary scaling, improving significantly with more examples. However, at the 32-shot mark, the performance gap widens, suggesting limitations inherited from the training data. Despite these gaps, the open-source pipeline achieved 89% of the performance of the corresponding proprietary model. The framework successfully validates the in-context visual scaling paradigm, proving these results can be replicated using publicly available components and code. Evaluations also reveal persistent weaknesses in visual question answering that affect the entire open-source ecosystem. Specific failure modes appear when the model processes complex scenes through its cross-attention layers. The models struggle with numerical counting and often answer questions about the central object in an image rather than the specific, non-central item requested. Additionally, the autoregressive nature of the model leads to verbose answers. These are often penalized by the exact match criteria used in standard VQA metrics. The Open Flamingo framework provides a functional blueprint for bridging vision and language, establishing the necessary intervals and token injection methods to create a working model. Open Flamingo establishes that the structural framework for interleaved multimodal models is reproducible. Closing the remaining performance gap with proprietary models now depends on refining the density and quality of images within open-source training sequences.